Okay, so in this session, we will start understanding the common source amplifier, which is designed using the potential divider method. We have using potential divider method. Is usually known as PDM method. And we're going to take simple common source amplifier. So my common source amplifier is basically my simple N MOSFET would act as a common source amplifier. So what I'll do, I'll take an NMOS and I'll attach PMOS as a load. PMOS will be acting as a load and my output I'll be taking it over here. Now, if you observe, my input is given to this MOSFET, NMOS, which is basically acting as an amplifier. And if you see, this is my gate, this is my source, and this is my drain. Uh, my input is given between gate and source, whereas my source is common. And here, when the source is grounded, and my output, I'm also going to take the output between drain and source, and here also my source is grounded. So in both the cases, my sources are common for both input and output, and that's why we call it as a common source amplifier, because source is common for both input and output. And this PMOS here, I'll be using it to ensure that constant current would be flowing in my NMOS such that my NMOS is always biased in the saturation region, because we know that for an amplifier or for any MOSFET to work as an amplifier, I should ensure that that MOSFET has to be in the saturation region. And for that reason, I should bias that MOSFET into saturation region. And there are multiple ways to bias it. And one of the simple ways to bias is to use a simple PMOS. I'll give you some constant voltage over here so that I'll ensure that this PMOS will be producing some current, and that current is a constant current. And that same current would be flowing into my NMOS, thereby making my NMOS also go into the saturation region. So that is basically the idea over here. So let's try to get into some straight away into the design concept. So I'm going to design the common source amplifier using potential divider method. And the given parameters here are, let's say, the power is being mentioned as 250 microwatt, and the VDD, let's say, 1.8 volt. That means we have to design this amplifier which consumes at the most 250 microwatt of power or less than that. So that is my basic agenda. Okay. So before we actually proceed, what does the potential divider method does over here? So when I say VDD is 1.8 volt, so this VDD has to be divided equally over here. So it gets divided over here. Later we'll see whether that division is being happening or not during the simulation. But this VDD, because it is 1.8, at the drain point here, my VDD would be, or this voltage would divide into 0.9 volt, and then here it would be 0. So this is basically the potential divider, or voltage is getting divided. So that concept I'm going to use. So to start with that, now here I don't know the sizings of the MOSFET. So basically I don't know the W and L ratios of the MOSFET. So those are the very important thing over here to figure out W and L. So I need to figure out W and L over here. So for that, first step, I'll choose. So I need to find my W. So what I'll do, I'll choose L equal to 4 times of the technology over here. So basically, I just want to have more value of L. So basically, my technology is a 90 nanometer technology. So 4 times of that would be approximately 360 nanometer. So I'm going to keep it as 400 nanometer. So my L, I'm going to choose it as a 400 nanometer. Now this is basically the design per se. Usually we take the L to be certain amount of greater than the technology node, whatever we have. So since we are using a 90 nanometer, it would be better to take some X times more than that of 90 nanometer. Then we need to start sizing the NMOS. There are two MOSFETs, NMOS and PMOS. So let's start sizing the NMOS. That is basically to find the value of W and L. L anyhow we are fixed to 400 nanometer. Let's try to find the W for NMOS. Okay. Now let's consider only NMOS from the above figure and let's redraw it. So when I redraw only NMOS, so my NMOS structure, so this is my V and here is my output, which is now having 0.9 volts due to the potential division method, and this is being grounded. I am going to choose when I do the simulation to find the value of W. I'll do the parametric analysis. So basically, I'll try to sweep the value of W. For that, I'll take W value is equal to W only. So this is what I'll choose. And for a particular range of W, I'll try to figure out what value of W is suitable such that I'm going to get a proper value of W that is collectively help me in getting the proper outcome for the amplifier. Now, before that, here we also now should ensure that what is the current. So basically, this would be my circuit which I'll be using to do the simulation to find the W. Now to do this, I need to do certain amount of things over here. So before that, I get into the simulation. Let us try to figure out, and I'm going to write an equation. Vg is equal to Vs plus Vt. If you see over here, plus 5% of VDD. So this is basically my gate voltage equation. So if you see whatever the entire setup we have here, if you see my standard equation for my gate voltage would come around Vg is equal to Vs plus Vt plus 5% of VDD. Now, if I use this entire equation, I'll be able to figure out what would be my Vg because I need what is the value of Vg to be applied to get into the simulation. So to get that Vg, let's try to find the value of, let's find the value of Vg and by putting all the values of these things. So Vs, anyhow, a source is grounded, it is 0. And also, I need to find Vt. So now to find Vt, yeah, to find Vt, I need to run dummy DC analysis for my NMOS, then I'll be able to find the VT. So that also I need to get it from the simulation. So I'll do that and get the value of VT and that I'll put it over here. Then 5% of VDD, which is 5% of 1.8 would be 90 million. So that I'll lose. So what is the value of VT? So let us try to quickly get into that. So now I have a couple of things ready with me already. So this is basically my NMOS, which I just draw over here. See, this is my NMOS. I have input where I am applying certain constant. Uh, uh, Before that, I need to find dummy DC analysis, right? So let's try to do that. So what I'll do is, like I mentioned, I'll choose the value of W as W and I'm going to keep the value of L as 400, and this voltage is 9.9. That means it is 900 milli, because if you see over here, this is 0.9, and I'm going to keep this as, let's say, let's quickly launch this. So this will be my dummy DC analysis. And let's choose for now the value of W to be equal to 2 micro. Let's run it. So once the run is done, we go over here, results, DC operating points. If I click on this transistor, scroll down, I'll come down over here and I'll see the VTH for that MOSFET is equal to 199, which is almost equal to 200 milli. So here, from here, I'll be able to get the VTH value. So that's how basically my dummy DC analysis goes. Now, let's get into over here. So I see that VTH is equal to VT is equal to 200 millivolts. So that 200 milli, I'll put it over here. So based on that, my VG would be equal to 290 millivolts. So that would be my VG. Or I can say approximately I can make it to 300 millivolts. Yeah. So for VG is equal to 300 millivolts, let us try to now sweep the value of W. Now, for what value of how should I figure out the value of W? I should have certain condition, right? So to understand that, basically what they have done. So if I say this as step number 3 to find the VT, let's go to step number 4. So in step number 4, so basically I need to find width of the NMOS. Now, because power has been given, so I know P is equal to VI. So based on that, I can figure out what is I, which is nothing but P by V. So power is 250 micro. Sometimes they will give power and sometimes they give the current itself. P is 1.8. If I solve it, I will be able to get I is equal to 138 microampere. So which I'm going to approximate it to 100 microampere. So that means if I try to design my entire circuit for a current of 100 microampere, definitely the outcome of the amplifier will be having power consumption of less than 250 microwatt. So that means consider I equal to 100 microampere and then find WN. So that means this is the max value of current, and choose this value of current and sweep this particular circuit from a particular range, such that at what value of W or for which value of W I'll be able to get the 100 microampere of current. So that would be my value of W. So let's try to do that in clear understanding. So basically what I meant was, so here anyhow we got the value of VGS, right? So I'll put it as 300 milli, which we got it over here. Now everything is same. W is also, I'm keeping it as W. So now with this value of VGS of 300 milli, let us try to sweep component parameter. I'm going to select the component parameter, this MOSFET NM1, and my parameter would be W, because I have mentioned the value of width as W. So basically what does that mean is I'm going to vary my width from 2 micrometer to 50 micrometer, and I'm going to perform the DC analysis. DC analysis is going to give me the current, that is a drain current. That means for what value of drain current, which is equal to 100 microampere, for that 100 microampere, what will be my width? So if I am able to get that particular value of current and W, I can fix up the W. So basically, if I just now run it, the outcome would be this one. So now here, if you see, this is width versus current. So now I'll press H horizontal line, and on this horizontal line, I'll click and I press on the Q. It will open up this particular marker window. I'll set this y-axis position to 100 and I say OK. So this is cutting this axis, this graph at particular value. If you see over here, 100 microampere is cutting. I'll just press M over here. It will mark. So at exactly 100 microampere, my width of the MOSFET is coming to close to 20 microampere. So 20 micrometer. So 19.7 means 20 micrometer. So that means, or I can say 19.5 micro. So that means to generate 100 microampere of current, my width of the MOSFET should be 19.7 micrometer. So that is basically how I figure out. So once I do this, so here the fifth step would be to do DC analysis for VG equal to 300 milli, and then sweep W from 2 micrometer to 50 micrometer. We get W equal to close to 19.5 micrometer for 100 microampere of current. Why I took 100 microampere? Because 100 microampere is the current that I obtained from this power equation. So that's why I'm mapping my value of width for 100 microampere. So this is how I fixed up my width of my NMOS. So now on the same grounds, we need to do the sizing for my PMOS. Sizing for PMOS. Now, when we do the sizing for PMOS, we should be taking the PMOS only, so upper circuit. So if you see, this is connected to VDD, there is a 0.9 volt and there is a V bias voltage. So let's try to do that. So I have my PMOS, this is 1.8 volt, this is at 0.9 volt, and this is at VB. Nothing but my VG. Get voltage. So again, let's try to use the voltage equation. VG is equal to Vs minus mod of Vt minus 5% of VDD. So now here the VG or the bias for this particular PMOS would be Vs. Now Vs in this case, it is at source is at 1.8 volt. Earlier it was at 0.9 volt, right? Sorry, the source was at grounded. So here the source is at 1.8. 1.8. We have already figured out the threshold voltage, 200 milli minus 5% of 1.8 would be again 90 milli. If I solve this, the gate or the bias voltage for this PMOS, I'll be able to get it as 1.8 minus 290, which is close to 1.51 volt. So that means use this VG as a value of gate voltage for this PMOS, and then try to do the sizing. So let us now get into, I'll just minimize this one. I'll just close this one. Let me close all these things. Yeah, so let's get into, so I have already the figure ready with me. So yeah, so this is my figure which I just drawn over here. See, the upper source is at 1.8, drain is at 0.9. So exactly the same way I have written over here. This is at 0.9, which is nothing but 900 milli. This is my DC supply, and the source is at 1.8, and then the gate should be at 1.51, again the DC supply. And my width is, again I am going to put it as a small w, because I'm going to find out width for this value of L. Okay, pressing F would fit into the screen. Okay, so check and save, launch ADL, copy from cell view. I'll give initial value for W as 2 micrometer. Analysis, I'll do the DC analysis, save operating points, component parameter. Now this time it will be my PMOS, and the component parameter name is W. And I'm going to sweep from 2 micrometer to 50 micrometer. And let's say I'll just give it as a new window. Outputs to be plotted. Select on the design, and I'll choose this value of source current or drain current. Yeah. So now if I run it, I should be able to again get a plot of width versus current. Now this time it is for the source. Again, I'll mark it as H, horizontal line. I'll press on this, I'll make it as Q. The property is open. I'll mark it to 100 microampere. It will come over here, and if I just see, it is somewhere around, yeah, 43 point, yeah, somewhere around 43. So I get sweep W from 2 micrometer to 50 micrometer and run DC simulation. That will be my 7th step. We get W is equal to close to 43 micrometer, and what was here, it is 19.5. And again, this is also, we got it for I equal to 100 microampere. So now my PMOS W is 43 micrometer and MOS W is 19.5 micrometer, and L has been fixed. So now once we know all these things, I can easily go ahead and design the main circuit. So if you see, this is my main circuit, which was drawn over here, right? So if you see over here, yeah, if you see over here, so I have taken a PMOS with a width of 43.5, because 43.5 micro cannot be fitted over here. I took 14.5 as a finger width, and I took the fingers as 3. So that marks as 43.5 micrometer. And same, sorry, and same thing for my NMOS. If you see 19.6 or 19.5. Then I have given the basically the inputs, and then we'll be able to do the simulation. So this is basically the overall sizing of my PMOS and NMOS. And I'll just explain you the inputs, various inputs what I have given. So because NMOS is going to act as an amplifier, I'm going to give all my inputs to the NMOS. So if you see, DC voltage is 300 millivolt, because this is the minimum DC voltage so that my MOSFET enters or MOSFET turns on, because that is my threshold voltage. That's why 300 millivolts is the DC voltage I have given. The AC magnitude has been given as 1 volt. That is the sinusoidal peak voltage. This is the DC voltage which is given to bias this PMOS. And then I have taken 10 picofarad as a load, and rest all is the same thing. So now quickly let's try to run one small simulation before we actually run the amplification simulation. Let's try to run a simple DC analysis, and let's try to plot the current. Let us try to do that once. So, or else let's do this one. We anyhow we will be, yeah. Let's try to do some dummy DC analysis on this first. Yeah, dummy DC analysis, and let's run it once. For dummy DC analysis, I'm not going to choose any outputs, anything. And, yeah, once the dummy DC analysis is done, if you just see, all the node voltages would be seen over here. And like I told, the potential should be divided. So this was 1.8 volt, and here I was telling it will be coming down to 0.9, that is 900 milli. And if you see 909.35, so that means the potential is being exactly divided by 2. So that's why I can say that this method is perfectly working fine as a potential divider method. That's what I just wanted to check with a dummy DC analysis, and that I checked. So here you see my VDD is 0.9, 1.8, half of that would be 900 milli, which is close to that, which is 909 millivolts. So it is working as a potential divider. Now, once we are done with these things, then we can go ahead and simulate this final outcome, which is basically plotting of your input and output signals. So that we'll try to understand once we run this entire simulation for the transient analysis. So that is basically the other aspect of looking into what is the gain and all. Let's try to look into that.